Where's Mr. Sams? He's gone. What happened to him? Oh, I know. Maybe I can make him appear somewhere if I use the gong. I'm looking. Where's Mr. Sams? I don't see him. Where is he? There he is, Mr. Sams. And here he is again. Huh, how did he get there? And he's back. How did you get from there to there? Ah! How did you get there?
Quantum mechanics.
Quantum mechanics.
Yes.
Like it's like you were there and then you were
somewhere else. Yeah. But never in between.
But you were never in between.
No.
How'd you do that?
Hey, the power with the gong.
Yeah, well, yeah, we have the gong with us today.
Yeah.
It's pretty cool. Yeah.
And the gong mallet. That's a beefy mallet.
Don't hit me with that.
Hey, used as a weapon.
Ah!
All right.
So, hey, what are we talking about today? Quantum mechanics.
Yeah.
Mr. Sams appeared in various places around the room and used the power of the gong.
Oh, yes.
And it's very powerful. Yeah. So we're talking about quantum mechanics today. So I guess we should get at it, huh?
Yeah.
All right. Hey, big question today. You're trying to figure out where is the electron in the atom?
Where's the electron? It's kind of like Where's Waldo, but with electrons.
Yeah, where's Waldo, or what was the other one? Carmen Sandiego.
Oh, yeah.
Where's Carmen Sandiego? Yeah, it's kind of one of those things.
Is that game still around?
I have no idea.
I played that when I was in elementary school.
I taught
Version 1. You taught with it? He's old.
I'm an old man. Okay, so where's the electron in the atom? That's the question today. Okay, and the answer, of course, is really simple, right?
It is. We don't know.
Actually, the answer, yeah, that's really the answer, is we don't know.
It's a very easy answer.
But the answer, actually, I say, is somewhat complex. Because we can't actually exactly say where the electron is. We can only say where we think it is. Probably. Probably be?
Probably, yeah.
How about likely? It will likely be. I think that's the word I was looking for. Likely be. We can't actually know exactly for certain where the electron is.
No. And when we define these orbitals that we're going to talk about, we usually talk about in terms of 90%.
It's the 90%
Where is it likely to be 90% of the time?
Yeah. Hey, this is developed by a guy named Werner Heisenberg. He was, and Louis de Broglie, and Erwin Schrödinger. Did I say that well?
Yeah, that was nice.
Yeah,
I like that.
Schrödinger.
Nice rolling
De
R.
Broglie and Heisenberg. Kind of like the Hindenburg, right?
Not quite.
Not quite.
No.
All right, sorry, we shouldn't make fun of these very, actually, brilliant people.
Yes.
They were amazingly brilliant.
Yeah, much smarter than us put together.
Yes, indeed. All right. And this is this dude Schrödinger.
Yeah.
I actually need the umlaut over the top of his name. So the Schrödinger made an equation from the hydrogen data. Do you remember the hydrogen data from yesterday?
That's the stuff that Bohr put together, right?
E equals negative 2.178 times 10 to the minus 18 times z squared over n squared.
I remember that.
So he did all that stuff, and he came up with some answers.
Yeah.
And you know what he got? You know when you do like math and you come up with an answer, an equation? Usually that's a
line?
It's a line, but guess what? He did not come up with... His answers were actually shapes.
Interesting.
And those shapes were actually not solid shapes. They were like hollow, but they were, we call them probability distributions. Now that makes a lot of sense, doesn't it?
Oh, of course.
A probability distribution.
Yeah, it's where something is probably.
Yeah, well, with 90% certitude.
Yeah.
Now, the math of this, actually, let's talk about that. The math of this is very high.
Yes.
It's like advanced calculus.
Plus some.
Actually, uber advanced calculus. Is that a word, uber?
I think so, yeah.
Okay, uber advanced calculus. Now, have our students had calculus?
Some maybe.
No. Uber advanced calculus?
Probably not.
Probably not. So, the good news is...
We probably haven't had enough math to do that either.
We're not good enough with the advanced calculus ourselves. So, we like that Mr. Schrödinger solved it back in the 1920s.
Yep.
And these are the answers.
Yeah, I like pictures.
We get a picture.
Yeah.
So, there are different shapes. Now, the shapes are called orbitals. Now, that is a residual of Mr. Bohr's model, where he thought that the electrons orbited the planets like, orbited the nucleus like planets orbit the sun.
There we go.
That's what I was trying to say.
I know.
But the reality is they don't orbit nothing.
Nope.
they exist in shapes. And so if we look at this shape, which is called the S shape, which stands for spherical,
Sphere.
there are different shapes. So the 1S shape right here, there's the 1S shape, and that's an S, same shape, it's bigger. And there's the 3S shape. And actually, we should actually visit about this. This right here, if I were to look, let me change colors, I think that'll be better. The 1S shape is a solid, not solid, it's a hollow sphere. And then the 2S shape, most likely it is in this area right here, but there's also a probability that he could be inside here. But he couldn't be in between here where the white space is. And those are called the nodes.
Right.
So you might have remembered back if you took last year's class and if we talked about it, that we had these spherical shapes, and we didn't talk about the nodes.
No.
Advanced topic here, ladies and gentlemen. There are nodes.
Right. There are places where it can be and where it can't be, kind of like me when I was popping around in the classroom earlier.
Yep, indeed. Okay. Now the second shape are called the P subshells, and they look like this. Somebody used to say they look like a dumbbell, like Arnold Schwarzenegger lifting weights.
Did you just call Arnold Schwarzenegger a dumbbell?
Well, maybe so. He wasn't always the smartest guy, but I guess he's governor or something.
He is
now.
governor of California.
Yeah, at least
he was my governor. He signed my teaching credential. Well, his copy of his signature is on my teaching credential in California.
So they kind of look like a dumbbell.
Yeah.
I'm not sure I'd call that a dumbbell. But anyways, this is the P shape. And there's actually three different shapes. There's the one that's on the x-axis called the PX, the one on the PY on the y-axis, and the one on the z-axis. And this is sort of just a... And this picture right here, if you look at it, actually has like little dots. It almost looks fuzzy. It's as if it's a bad picture. But that's kind of a point here.
Yeah, there are no really defined edges of these. Again, we're talking about probability, where it is 90% of the time. So... we can't really draw a line if we're only certain about where that line is 90%. We're 90% certain about where that line is.
Indeed. Another thing that we should also make a note of that's kind of odd about this is that it's as if the electron is everywhere on the surface of this shape at the same time. And that's weird.
It is very.
How can a little particle that's itsy bitsy be here and also here at the same time? And here, and here, and here, and here, and there. It just is. Actually, it has to do, frankly,
That's
folks,
back to the wave property.
the fact that the electron is a wave. Remember we learned that matter are both waves and particles in the last podcast. So it's the fact that it's a wave, and it's what we call a wave function. And actually, the probability pattern, if we want to get totally correct, is actually the square of the wave pattern. How's that for crazy? Okay.
That's crazy.
It is crazy. The third type of shape is the D shape. Looks like a four-leaf clover, if you ask me.
Except for the donut one.
Except for the donut one. I like the donut one.
I like donuts.
So these are the four-leaf clover ones on different axes, and this is a different shape. Okay? And lastly, actually, not lastly, but it is the last one I have a slide for, this is the F shapes.
Yeah.
And there are 7 of them, and I don't even know what to call these things.
Far out.
Far out. Oh, good. Yeah, you go far out. There's actually G shapes. Did you know that?
I did, but I have never seen a diagram.
I saw a picture
before.
on the internet, and they were even farther out.
Farther out, like
greatly far out.
Groovy.
Groovy out.
Ah.
There you go. Yeah, I get.
I'm sorry. I'm trying to use some words that you might be familiar with.
Groovy, man. I'm way cool with that. Yeah.
He's old.
I'm old. But where indeed is that electron?
Well, we can sort of kind of know it if we know less about something else.
You see, there's this guy by the name of Werner Heisenberg, one of those brilliant dudes, and he said, in fact, it's called the uncertainty principle because the idea is that you can never exactly know where the electron is.
Right.
So that
the more you know about its location, the less you know about its momentum.
So there's actually an equation that relates to this, and it's delta x times
delta
mv is greater than or equal to h over 4 pi. What in the world is that?
I don't know.
All right. Delta x is your position. How well do you know where the electron is within a particular number of meters, or centimeters, or nanometers, or whatever? And this is the mass of the object and its speed, because the electron ultimately is moving. This is, by the way, when you take m times v, it's actually called the momentum. And it's greater than or equal to h over 4 pi. And h, if you recall, is Planck's constant, and it is a very small number.
Yes.
10 to the minus 34th. And so what you can do is you can solve for, if you do the math, I don't know if we do you want to do the math?
Nah, let's not do
If
that.
you do the math, what you're going to do is you're going to discover that the value for delta x is usually in the neighborhood of about a meter for an electron in an atom. Now, why is that a problem?
That's huge.
A meter is like 3 feet, right? And 3 feet is much bigger than an atom.
Uh-huh.
An atom is, of course, in the nanometer range. And so the ultimate answer is, it's kind of like the old joke. If you ever go to you go to a hotel and they've got this sign on the front of the door. You ever been to those hotels and it says, George Bush slept here or Barack Obama slept here, one of those type of things? Well, they have Heisenberg slept here. Maybe.
Maybe.
Because it's the Heisenberg uncertainty principle, because you never know.
Right, because the more you know about the position, the less you know about the momentum. The more you know about the momentum, the less you know about the position.
So that's probably as clear as mud, frankly.
Yeah.
But the point is that you can never know the exact position of an electron. And if you did, it would have moved.
Yeah.
So that does create some interesting...
kind of like Mr. Sam's.
Yes, like Mr. Sam's at the beginning. So Mr. Sam's... Okay. We're going to use the white-colored ink. Okay. Now, the shapes come from a mathematical equation. Okay? Now, I'm not going to write the equation, but it has variables. Okay? So in a mathematical equation, usually you have like x's and y's and such like that. Mm-hmm. Well, this has variables, and these variables are called...
Quantum
numbers. And what I really want you to realize is it's as if every electron has an address. Every electron has an address. Okay, there are 4 different quantum numbers, and the variables are L, M sub L, and Ib sub S. And each of these represents something else. N is called the principal quantum number. I'll use the number symbol to not have to write that down. L is called... L's got a funny name. It's called the
azimuthal. A-Z-I-M-U-T-H-A-M.
And that's the quantum number. And M sub L is called...
Magnetic.
Oh, see, M for magnetic, yeah.
Yeah.
Magnetic quantum number. And M sub S is the...
Spin projection.
We just call it the spin. The spin quantum number.
Yep.
Now, the reason we have a spin, by the way, is the fact that the electron is actually spinning.
Yeah.
So the individual little, if you think now back to the electron as a particle, it has a spin, kind of like the world spins on an axis, the Earth. And so these are the names of these, all right? And that leads us to this table that you actually probably have a little bit more filled out, but I left it unfilled on purpose for us to kind of talk it through. I think would be good. All right, let's change to a new color. All right. In the principal quantum number, of course, that is an N. And the value of N is somewhere, N is going to be 1, 2, 3, 4, ... It's an even whole number.
Yep.
Oh, an example, of course, N is equal to 1, 2, 3, etc. I guess I should have done that. That's fine. The azimuthal is, of course, the symbol is L. Mm-hmm. And this is, and actually this is the shell. We'll talk about this in a minute, I think, in another slide. This is the subshell. Actually, when you write subshell, I want you to write that this is the shape. Or you can say S, P, D, or F. And the number is always between L.
No, it's between 0 and N minus 1.
So it's 0 to N minus 1.
Yep.
All right, so if you have N equal to 3, L can be either 0, 1, or 2. Okay. All right, and I'll save a slide for that later. All right, and then M sub L is the energy shift, and this is always between negative L and positive L. So if L is equal to 2, M sub L will be equal to negative 2,
or
negative 1,
or
0,
or
1,
or
2.
There you go.
So there are 5 different options when L is 2. And the spin quantum number, which of course is M sub S, this is just going to be negative 1/2 or positive 1/2.
Yep.
All right, now I want you to think of this as an address for an electron. Okay, so let's kind of think this through. All right, so folks, what we're going to do, you've got this quantum number practice, and Mr. Sams and I just had a time out here, and we talked about that. I think we're going to do this after we do something else, so just bear with us. We'll come back to this, leave it blank. We're going to put something there in a minute. So let's just talk briefly now about the history of the periodic table. Periodic table was originally elements were grouped because of their similar properties.
Yeah.
Done by a guy named Dmitri
Mendeleev.
Mendeleev, if I'm not mistaken. You know that my fantasy football team,
Uh-huh.
which I got third for the second year in a row, by
Yeah.
the way, this year. You know what they're called?
Something with Mendeleev?
Mendelev's Revenge.
Oh, nice.
And I need to revenge next time because each time I get like
I think
third
so.
place. What's up with third place?
I don't know.
You get paid for first place, you know? You get paid for second place,
But not third.
not third. So I got third
No.
place 2 years in a row. Yeah, last year because of a stupid snowstorm. Okay. Yeah, so this was Mendeleev's periodic table right here. This was his table, if I could see here. This is Mendeleev's periodic table. And the thing that's kind of cool about his periodic table is that he left some blank spaces. You see a blank space here, and particularly here. And he predicted that those elements, because he did this in the 1800s, late 1800s, he said someday we're going to find these two elements. And
Lo and behold.
lo and behold, he said there'll be some element with these particular properties, this melting point, this molar mass.
And here's where it's going to fit on the
and,
periodic
this-
table.
and he was right.
Yeah.
And so it was very predictive. But he used the physical properties of the elements, their melting points and their boiling points and their reactivity and these kinds
Masses,
of things.
things like
And masses, and they put them all together, and that's how he made the periodic table. It's actually orientated in the different direction that you would be. No, it's not.
No, that's right.
Yeah, so here's like sodium, lithium, sodium, potassium, rubidium. He's got silver and copper here. He didn't know what to do with them, and cesium. So he has some ideas, and of course we now have a modern periodic table. Here's the two elements that he predicted. In 1871, he predicted that you would find an element like this. Element number 72, this is the example of germanium right here. And 1871 he predicted it, and this in 1886, pardon me, some scientists figured out, and these are the numbers, and if you look at this table, he almost exactly predicted each of these numbers. And he was very correct. Or it was just like the mysterious chemical, you know what they call
It
it.
ended up being germanium.
And we now call it germanium. So everything was pretty spot on. Maybe his boiling point was a little bit off, but he was awful close on almost everything else. All right. Now, that leads us to the Aufbau principle. What's that, Mr. Sam?
Let's see here. That is the one where you fill the lowest energy first.
Yeah, so there's a bunch of rules. Did I get into something? Okay. There's a bunch of rules when we're trying to do things called electron configurations. And you might have had this last year. You might not have. If you haven't, we'll talk it through. What you do is you read the periodic table like a book.
Left to right.
You always read it from left to right and top to bottom. Turns out when we look at the periodic table, we discover the periodic table has it has to do, the shape of the periodic table has to do with the electrons that are filled. Okay, so when we read like a book, the first element right here is hydrogen.
Mm-hmm.
And the first orbital that we'd fill, the first shape, as we talked about a little bit ago, is the 1s shape. And then the second orbital, it's actually the same orbital, for helium is also the 1s shape. So I'm reading like a book, left to right, top to bottom, so boom. Now we have to skip a big space here, but let's just deal with it. Okay. Then we jump, and the second level is the 2s level, and then we skip this space, and then we go to 2p.
2p.
And what we're doing is we're figuring out in 3s.
Mm-hmm.
We skip this whole space through here, and we get 3p, and then we jump down to the next line of the book, if you will,
Making sense so far.
4s, and then now we do another thing. It's kind of odd here.
Junk.
This is a 3D. Now, if you like to
Yeah.
think about it, some people like to have the idea, this is 1, and then 2, and then 3, and then 4, and this is a 4, and this is a 3. Why is that? Well, because it is. I mean, there's not.
Yeah. The 4S just has less energy than 3D. They
Yeah,
fill low energy to high.
Yeah, and so we can actually read it like a book, and we can figure out the filling of the orbitals by just reading the periodic table like a book. Now, we should make a brief mention of this spot right here and this spot right
That's
here.
where the F's fit in.
Because the 6s right here, right between here and here, if you look at your periodic table, if you have in fact, it would be a bad idea to get your periodic table out.
Yeah.
And we actually have one right here.
Yep.
But if you look here, this is element 56, this is element 57, and this is element 72.
There's
Whoa.
a big hole.
There's a big hole. So
Yeah.
actually right through here,
Yeah.
these elements right here, these called the lanthanides and the actinides fit. So the
Do you
periodic
know why
table.
they put the F orbital down at the bottom like that, Mr. Bergman?
Yeah, actually I do. Because they wanted to fit on a piece of paper
Yeah.
that's 8.5 by 11. Because actually the real shape of the periodic table, do we have a blank screen somewhere?
I don't know.
Yeah, hold on. So actually, here's the picture. We're at Wikipedia.com, and you can see the expanded periodic table here. Here's, in fact, the G block right here. We talked about those.
Yeah.
That's a possibility. These are elements that haven't been discovered, actually. And then here's the F block, and here's the D block, and here is the P block. So this is the real periodic table. That would not fit very well in an
No,
8.5
not
by
really
11
well.
piece of
Be
paper.
hard to use.
It'd be hard to use. So they pull particularly the F ones, lanthanum and all these other out. And so that's the reason behind all that. So that's what the periodic table should actually look like. So, all right. All right, let's do boom. All right, let's do some practice. Okay. So now there's actually sort of a notation system that we use. Let's take the simplest element of all, hydrogen.
All right.
Hydrogen has one electron. All right, now we take a box. Now we write a box because that represents an orbital. Now in this case, the very first orbital, so we go back to this screen, the very first orbital that we would use is the 1s orbital, right?
Yep.
I'm reading the periodic table like a book and write 1s. Now technically that is a sphere, okay? But we make a box which represents any particular shape, whether it's a sphere or the dumbbell-shaped ones or the clover ones or whatever.
Donut.
Or the donut. Yeah. That's getting towards to lunch, isn't it?
It is.
And then we use an arrow to indicate how many electrons are in the box. Okay?
All right.
And so if you put one electron in the box, that then is that's the electron configuration of hydrogen. So the question at the beginning of this podcast is, where are the electrons, most likely at least? And we would say that there is one electron in the 1s level. Okay? Does that make sense, guys? So that it's in the 1s level, and there is one electron.
There it is.
All right. You know, I'm not sure we talked too much about the rules. Have we talked about the rules?
No.
You know, we should probably do that. Have we done that?
Like Hund's rule and all that
Yeah,
stuff?
all those rules. So let's do
Those
that.
aren't on our sheets.
All right, so folks, if you don't have this in your podcast, actually I need to do this, don't I? If you guys don't have this slide or information in your on your paper, you need to add it. Okay? Aufbau principle. Okay, so like for the fourth time, I want you to write this thing, the Aufbau principle. The Aufbau principle says that you fill the lowest energy level first. Okay, so
Yep. 1s, 2s,
2p.
2p, 3s, 3p, 4s, 3d, 4p, and so on.
Yeah, and Hund's rule says
You got to put one electron in each shape first before you can put it in two. I don't know if we mentioned this, but each little shape, each little subshell can only accommodate up to 2 electrons. It can have
Each
0,
shape.
1, or 2. So the way I look at it is like a school bus. If you're filling a particular energy level, like let's say like the 4D, okay, there are 5 slots that you can put them in, and we'll talk more about that in a minute. But let's say that's a school bus, and the school bus driver says, as the kids come on, you got to put 1 kid in each seat before you sit with 2 in a seat. He's a real tyrannical bus driver. You can't sit with your friend. You just have to come in, fill them up in order first, and then once all the seats are filled with 1 person, then you can go through and fill with 2.
Or, you know, might think of it this way. Would you rather sit next to your friend or not? Maybe they're like you're in 3rd grade and they all got cooties or whatever.
Oh, yeah.
You know, and so they don't want to sit next to each other anyways. But, you know, when you have to sit next to them because there's no more room, then you will. You know, whatever.
Yeah.
All right. And the Pauli exclusion principle says that each electron has its own unique, I'll say address in quotation marks. Or actually, technically, it has its own set of quantum numbers, which you'll see in just a little bit. Okay? So, now let's go back to our practice. So we did hydrogen.
We did hydrogen.
So let's do something a little bit more complex.
All right.
Let's do lithium.
Lithium, right below hydrogen.
Not very hard because, of course,
Nope.
lithium has just 3 electrons.
Yep.
And so my first orbital that I would fill, let's go back to that
By
screen.
the way, his little 3 there should be down on the bottom.
Yeah, you're right, actually.
Yep.
Is that the first orbital is the 1s orbital, right?
Yep.
Left to right, like a book. All right. And so for the 1s orbital, all right, I am going to, I can put 1 electron and 2 electrons. And by the way, some people ask about the arrows. The arrow up represents that the electron is spinning in one direction, the arrow down in the other. And is there a rule about whether you put it up first and then down?
Nope.
No.
Doesn't matter.
And so I label this, all right, 1s. But I have 3 electrons, but
You got to fill the 1s first, and then you go on to the
what do I?
2s.
Because I got 3 electrons.
Right,
It's like
you
I
got
got
one
3 to spin. I got to figure out where that next one goes.
Yep. So we
And
move
I'm making a
on to the
box.
next.
And so the next box, if you look right here,
Is
right
2s.
there is the 2s box. And so I'm going to label that 2s, and I'm going to put an arrow up. And by the way, just as a note, this is the lazy chemist arrow.
Yes.
All right, because there's less T strokes. All right, we would say 1s2.
Because there's 2 electrons in it.
And then 2s1.
Because there's 1 electron in that one.
You get that? That's
There it
not
is.
too bad.
No.
Let's jump up and do, say, fluorine. Now, fluorine is element number 9 on the periodic table. I'll put it in the right place there for you, I understand.
Hey,
All right, and the first orbital that you would fill would be the 1s.
1s.
You always fill the 1s first. So I've got the 2 electrons. All right. The next orbital we now know is the 2s orbital, and I will fill that up. 1, 2. Okay. Now the next orbital, right, 2s right here, I next jump up and I'm going to fill the 2p.
2p. Now if you look on the table, fluorine is the next to last one in the 2p. So Mr. Bergman would put an X right there, or write the F. There it is. That's the spot we're looking for.
All right, so what I'm going to do now, watch this, is instead of drawing 1 box, I'm going to draw 3 boxes.
Right.
And I'm going to put 2p on the top.
Yep.
Now,
S's have 1 box.
It's like this is the 2p, remember the X box, the Y box, and the Z box, if you will.
Yeah.
Now, how many electrons do I have to spin now?
You have 5 you need to put in there.
So I've got 4 already spent.
Right,
I got 5. So this will be the
more.
5th one. 5,
6,
6, 7. Now, folks, notice I separated them first.
Yes, 1 in each box first.
Now they have to sit on the bus
Yep.
with their friend now, or
8.
the guy with the cootie.
9.
And that's the answer.
Yep.
We would say that that's 1s2, 2s2, and now I'll say 2p, and I count them 1, 2, 3, 4, 5.
2p5.
2p5.
Yep. So S's have 1 box, P's have 3 boxes, D's will have 5, and F's have 7. 1, 3, 5, 7. Real
So
simple.
let's do now something a little more complex. Let's jump way up and do vanadium. The element of vanadium, element number 23. All right. Now, I have 23 electrons to spin. So I need to fill as many boxes until I get to the 23rd electron. Well, it gets redundant here at this point. You do the 1s box, that's 2 of them spent. You do the 2s box, that's 2 more, total of 4. Now I'm going to draw the 2p box. All right, put a couple boxes in there, so I'll go 1, 2, 3. Now the capacity of a p is 6. There's 2, 4, 6 of them, right? So that's 2p6. Now what's the next level
Next,
here?
we're at 3s.
So if we finished over here at 2p, we'll go to the bottom of the next line, and we're going to go to a 3s. So, boom, the next box is a 3s. And we will fill that as well. The next box is
3p.
a 3p box. So if we go back to double check that, 3s, we skip this whole section through here, and then we get the 3p. And this will get filled too. 1, 2, 3, 4, 5, 6. And actually, what are we up to here? That's the 3p.
We're up to 18 there. Yep.
So we've gotten to 18. Now the magic number for vanadium is 23.
Right.
So now we go to the next
Next,
line.
4s.
So now we jump down here to the 4s orbital. And so we draw another, S's always get 1 box, and that will be filled. So we're at 20 electrons,
Yep.
right? Now I have the next level, oops, wrong direction, and I want to now fill the 3D. Now this width here, if you look at it, is 10 wide. If you were to count 1, 2, 3, this here is 10 electrons,
Yep.
or 10 atoms. And so this is going to be a 5-boxer.
Yes, because 2 electrons per box.
So now I've got 5. And how many do I have to
We
spend?
got 3 more.
So I'm going to put 1 in each. 1, 2, 3, or 21, 22, and 23.
Yeah.
Now the electron configuration of that will be 1s2, 2s2, 2p6. You're filling each of them except for the last one. 3s2, 3p6, 4s2, 3d3. Now, I actually could have told you that it was 3d3 without having to do the whole thing, though.
Yeah, that's where I always start.
It's actually the best place to start. So
Yeah.
if you find vanadium on your periodic table,
Right
it'll be
there.
right here. You might notice it's 3d, and if you were to count them over, 1, 2, 3. So
Right.
the last electrons would end up at 3d3.
3d3. You
And
just
if
gotta
while I'm
fill
at
in-
that, let's
Oh,
take
yeah.
this one down here, and this is the element AT. right?
Astatine.
Astatine.
That is
Now,
either the rarest or the second most rare
Is
element
there-
on Earth. I
I
can't
didn't
remember
think
which.
I knew that.
Yeah.
Okay, in astatine, I can actually predict what the last electrons are going to fill
Mm-hmm.
for that one without having to do 1s2, 2s2, 2p6, 3s2, 3p6,
that's
4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 5d10, without
your
doing all
4
that.
Fs.
Oh, I forgot my 4fs.
Yeah.
This would be 6p5.
That's the end. Then there's a bunch of stuff before
There's
it.
stuff before it. Now, how do I know that? Because if you really think about this, on the periodic table, this is going to be the P1 block, if you will. This is P2, this is P3. This is by columns. This is P4, and this is P5. Always. So astatine would end in 6p5, but I could jump right up here to the 4, whoever this is, a bromine, I think, isn't it?
Yep.
This is going to be 4p5. So you can use it, it's almost like a grid where you just kind of read the thing. Now this of course works because this of course is the 4th period. That doesn't work with the D's. But if I wanted to grab a 5D one right here, hopefully this is not one of the exceptions. I don't think it is.
5D. Fourth from the end?
Yeah.
Iridium.
No, it's not. Okay, good.
Yep.
So this is what? This is going to end in 5D, 6, right? Yeah.
7.
7?
Yep.
Yeah, that's 7. Okay. Good. So you could just, it's like a grid, and then you can like do it.
Should we show them the shortcut?
Yeah, and there's like a cool shortcut. Yeah, there's a pretty cool shortcut. Yeah, so we should talk about the shortcut. All right, so let's do a hard one, Mr. Sams.
Okay.
Um,
Do we want to go in the F?
yeah, let's do uranium.
Okay.
Uranium element number 92. So we have to describe where every electron is in uranium.
We do.
So let's do it. Well, let's do it the long way, and then we'll do it the short way.
Okay.
Should we do it that way?
Yeah.
All right. So uranium.
Should we look and see where it's going to end first?
Maybe we should look at where it ends first. That's a
Yeah.
good idea. So if you look at where it ends, here it is. If you look at where it ends, uranium is how far over?
The third one.
This is uranium right here. So it's going to end in. Now it's down here. It's between here and here. So if this is 7s, this is 4f, this is 5f. So that's just going to be like 5f3.
Yep.
So that's pretty easy.
Yeah.
Boom. It's going to end in 5f3. All right. So if I get uranium 92, read it like a book, left to right, top to bottom. So the first box is the 1s box, and you're going to fill it. So we just have to keep going back and forth on this. So what we're going to do, folks, is read it like a book, left to right, top to bottom. So there's the 1s level. Let me change the ink color. Back to black. So 1s. The second orbital is 2s, and then 2p. So let's do 2s and 2p together. So we'll say 2s right here, and we'll fill that. And then we'll do 2p, and we'll fill that. 1, 2, 3, 4, 5, 6. The next one, you go to the next line. If you look at your periodic table, have that out. That's the 3s. And the next level will be the 3p level, and we'll fill that. The next level is the 4s level, and we'll fill that. All right. So if you go back here, there we go. 4s we're now. And then we're going to jump to 3d. Get the right screen yet. Now remember the D's are 5 long, so nice long box. 1, 2, 3, 4. And this is the 3D level. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10.
Do I have time to go get a cup of coffee while you're...
Yeah, this takes a while.
All right.
And this is 4P. And on 4P, you would go like that. Coffee at this time of day?
Oh, make coffee at any time of day.
4P6. We're at the end of the fourth line, right? So if we're at the end of the fourth line, now we are right here. We jump to the 5s line. And so that gets a single box for the 5s line, double arrow, right? And now after the 5s, we go to the 4d. It's kind of weird. It's kind of one behind. This takes a long time, doesn't it? We're describing every flippin' electron, is that a word, in the atom. And after we go back now to the 5p, and that's going to be 3 wide, 3 boxes wide. There's Mr. Sams back with his coffee. His coffee latte. All right, now after 5p.
You only got a 5p?
Sorry.
Oh, for crying out loud.
Go to 6s. All right, so we're almost there, though. 6s, and that's going to be just a 1-boxer. All right, we're almost there. Now if I go back to it, 6s. Now what happens after 6s?
Jump down, 4f.
We jump down to 4.
We're in the F's. We're almost there.
Now I'm going to make a 7-wide box. That's got a little bit crunch there. Oh well, 4f, 1, 2, 3. They give it 14 in this if you think about it. There's 7, 8, 9, 10, 11, 12, 13, and 14. And then, of course, after the F, you go back to the
D.
5D, right?
5D.
5D. Yep. 1, 2, 3, 4. So 1, 2, 3, 4. Why did I choose uranium?
I don't know.
Actually, if you can do uranium, you can do any of them. All right,
Yep.
5D. And now we go to the 6P.
6P.
It takes the whole screen to do this. Isn't that unbelievable? All right, 1, 2, there's 92.
Did we mention we're going to show you a shortcut?
Yeah, I hope so. And then after that, we go to the 7s, because we're now to the next line. So if we go there, so I did the 6D. No, I did the 6P. Now I do the 7s, right?
Mm-hmm.
And that's just filled. And now we jump to the
5F.
Finally to the 5F. So 1, 2, 3, 4, 5, 6. And how many am I going to put in there?
3.
3. 1, 2, 3. Done. So how would we write that? Well, we'd say, well, 1s2, 2s2, right? I'm just reading these things, right?
Yep.
2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10. I need more space. Can you do this? And then, what happens to 4d10? 5p6, and then
6s2,
6s2,
4f14,
4f14,
5d10,
5d10,
6p6,
6. Hard to do this by it's on the side.
7s2,
7s2,
5f.
5f3. Oh my gosh, that was long.
Mm-hmm.
Oh my Lord, have mercy. Now,
And now,
let's do the shortcut. Oh yeah.
for the shortcuts.
We love shortcuts because in the shortcut, of course, what you do is you go back to the last noble gas present.
Yes.
That is the last column on this particular periodic table, column 8A.
Radon.
And in this case, the last one was a radon. You always go back to the last periodic noble gas.
Yeah.
And so what you do is you put brackets and you write radon. Now, what that means, folks, is
Everything through 6p.
all of this that I'm circling, this is just brackets are in. Done. You don't have to write it all, you just write that. Much easier.
You know, they're all groaning right now going, why didn't you just show us that to begin with?
Because it's good to know the whole thing.
It is.
Actually. So then you do 7s2, because that's what happens after radon. After radon, you go to a new line, and you start the new line, 7s2, 5f3. Done. That's it.
The end.
And actually, if you turn in your paper, guys, to this sheet, you have this. It's hard to read probably on the screen, but it tells you everything. How's that? Tells you the whole electron configurations of everything. After, of course, each, it's the shortcut notation.
Yep.
They don't put the XE or the AR or whatever the particular noble gas is, but you have it right there.
There it is.
Okay, now actually this brings us to an interesting conversation. Okay, there are some exceptional electron configurations. That means those that don't fit your pattern, the ones that don't work right. So actually, if you look at this chart here, so look carefully at the chart on your paper, and if you find the copper family, actually the chromium family first. Find the chromium family, and if you were to think about this, what you would expect of the chromium family is you would expect him to be 4s2. Now it'd be, was it argon?
Argon.
Argon. 4s2, 3d4. But
It's not.
But it's not. If you look there, snot?
Snot.
Okay, it's not, yeah. Yuck. And so it's actually 4s1, 3d5.
Yep.
All right, so let's take a look at that. I'll go to the right screen here. What's going on with that? So if we were to do the chromium family and just do the argon thing and do the box notation, you have 4s and then you have 3d. All right, and there are a total of 6 electrons to give away. And it turns out instead of the 4s, this electron doubling up and going here, it spreads out like that. The reason being, and this is actually true of the entire chromium family, which is also called molybdenum and tungsten and seaborgium, is it has to do with stability.
Yeah.
And here's kind of a rule. Half or full sublevels are stable. And so, because the other option, if you think, the one that you would have expected would be 4s2, and then when you did the D, you would have 4. 1, 2, 3, 4. Well, that's like 4 out of 4/5.
Yeah. So close.
But it's not half.
No.
And so if we can do a half and a half, that's more stable than a full and a messed up one.
Yeah.
And so what it likes to do, some people have sort of thought of this electron here as sort of promoting itself to the 3D. That's fine to think of it too. But the point is,
shameless self-promotion.
yes, he self-promotes himself. Exactly. So that if you can get a full and a half, then you're good to go. The second one that you want to look at is the copper family. And if you look at the copper family, he also is odd in your expectation. Notice it's 4s1, 3d10 there.
Yeah.
And when you're looking at that, that's essentially the same concept. If you look at the 4s, he's only going to have one electron. But the beauty of that is it can make the 3d
Completely full.
completely full, because you'll have 10 electrons in the 3d orbital. And so you've got a full orbital here and a half full here. And that's more stable than having this orbital full and this one 9/10 full. So it has to do with stability of orbitals. So full orbitals are most stable, and half orbitals are also quite stable, or stable-ish. All right? So hopefully that helps you kind of get this. All right.
Okay.
Whew, this is going to be a long podcast.
Yeah, do we want to talk about Heisenberg at all and tie this back into quantum?
Yeah, we should probably do that. All right, now I want you to take your packets and turn back to the quantum number things. All right, now that we know about electron configurations, we want to do quantum numbers. So let's take, which one we just do? Copper. Copper, of course, we learned was argon, 4s1, 3d10. Right?
Yep.
And so the quantum numbers, that's that NL and ML and MS thing. If you want to look at this, if we were to draw the 4s electrons, there are 2 electrons in the 4s level, and in the 3d level, there are 10 electrons. So let me just draw what this would look like, of course, from the electron configuration perspective. And then let's pick a couple of electrons and see if we can describe their location from the quantum number. This is essentially the numbers in that fancied equation with the Uber calculus. So let's take one of the relatively easy ones. Let's take the first one, which is the 4s one.
Okay.
So we have an N would be equal to 4.
Whatever that big number is in front, that's your N.
N is always, that's the easy one, because always is the principal quantum number is the number in the front. And then L is actually relatively easy because it's 0. Because... And actually, this is something you want to write down when you do quantum. S, this is L here.
For the L quantum number.
Is always 0. If it's a p orbital, it's a 1. If it's a d orbital, it's a 2. And if it's an f orbital, it's a 3. And actually, if it's a g orbital, it's a 4. All right, so because this is an S, you go over to this table here, S is equal to 0. All right, and then the M sub L is always between, if you recall, it is between negative L. We don't have that on the screen anymore. Negative L and positive L. Well, 0 to 0.
Yeah, negative 0 and 0 is just 0. That one has
so it's actually saying that this box right here is the 0 box.
Yep.
And M sub S is the spin.
Right.
And actually, we're just going to say arbitrarily that if it's going up, arrow up, it's
Plus
1/2.
half.
And negative 1/2 if it was going down.
Yeah.
So actually, if you were to describe this electron, this second electron, it would be 4, 0, 0, negative 1/2. You see, this is the address, if you will. Think of it this way. N is like you live in Colorado.
Okay.
L is you live in the town of
Woodland
Park. M sub L is you live on the street, Piney Point. And M sub S is your house number. I won't say what my house number is.
You want to give me house number too?
312. There you go. So you now know where I live. So if you're watching this on the internet, don't send bombs or anything to me. Okay. Now, what if I wanted to describe, say, this electron right here in the 3D
Thanks
orbital?
for not doing mine, by the way.
Yeah. You don't even live in Woodland Park.
No,
so what's N going to
divide.
be? N will be 3 because of the principal quantum number. This is the Colorado address, if you will. So N equals 3. L is equal to
this is the d orbital,
so
2.
So it's going to be 2. M sub L is always between L, negative L, and positive L.
Right.
And the way I like to think of this box here is the negative 2 box, because it was 2,
Yeah.
right? And this is the negative 1 box, the 0 box, the 1, and the 2 box.
And he's just kind of sticking those in there arbitrarily, and it's not a big deal. A more common question that you might see is how many electrons can have the following quantum numbers. So if it gives you 3 quantum numbers, like if you stopped at a particular, like if you just put the 1 right there, then there's more options than.
Yeah. So M sub L, of course, is 1 because he's in the fourth box over. And again, that's sort of ish. I mean, that's correct, but it's an easy way to think about it.
Yeah.
And then M sub S, since it's going up, I guess did that one up, that would be positive 1/2.
Yep.
So this is the address, if you will, for this particular electron. So now you live in not the state of Colorado, but the state of Michigan, and you live in Grand Rapids, and you live on
Elm Street.
Elm Street, and your number is 72.
49. 72 is fine too.
42 is because that's like the answer
is.
to life and everything or something.
It is, and the universe.
So that helps you understand how to do this whole quantum number practice thing.
Yeah.
Good? All
Good.
right. So, James, are you
Yeah.
going anywhere?
I am. I'm leaving right about now.
Where'd you go? How'd you get from there to there? Mighty? And he appears as the mighty odd person. And that looks odd, like an ugly bunny rabbit. I don't know what's wrong with the man. Very odd. Very, very odd. And now he has vanished into the vapor, and he is now disappeared forever. Have a good time, and we will see you back